Thank you. Hello, I'm Gregory Morse, yeah, and uh, oh, oh, okay, uh, yeah, okay. So I'm Gregory Morse, and I'm going to be talking about something in a quantum compilation workflow, or dealing with optimizing quantum circuits. Okay, so we're talking about a search-driven strategy that we've developed, and two main results. One is about all partitions. This is a kind of the first result that was gained. So these are not necessarily in order of how impressive the results are. This is more of a mathematical result. And then this OSR guided uh, optimistic ensemble extension search. This is the kind of newer result that's come over about in the last 6 months and is actually needed to get this kind of be more useful. So we're going to look at this. Uh, okay. Uh, how to advance the. Oh, okay. Click. All right. So compilation is can be a search problem, and the way we can turn it into more of a search problem is instead of trying to compile a huge circuit, we can partition the circuit into small partitions. And when we do that, for example, to fit onto certain quantum hardware, okay, which will have some custom topology and it will need to do routing and other things, but doing the whole circuit obviously is too difficult. So partitioning it is a very good strategy to break the problem into smaller parts. And this actually will make this a candidate for all sorts of parallelism. And so there's all sorts of opportunities here for various things like GPUs or other hardware, even potentially. We've even run the simulator on Rock hardware, and Peter will talk about that next. So, oops, now it's working. Okay, so now basically the message we're trying to get across here is that if you can engineer the search strategy very well, you can actually use these type of partitioning strategies to achieve really good results. So the circuit basically we're trying to fit onto quantum hardware. There's actually another context for this, which is fusion. If you're actually trying to classically simulate a quantum circuit, you may want to fuse gates together to get a performance boost, but that's not really the main focus. The more impressive thing is to be able to actually compile circuits onto quantum hardware with the least gates possible. So we want to optimize the circuits, namely, especially the interactions like the C naught gates, okay? And so what we do is we want to get blocks that are small, okay? And so this will be in the 3 to 5 qubit range. And then we want to, at the same time, be able to simplify these 3 qubit to 5 qubit partitions so that we can use less CNOTs to represent the same circuit. And so, yeah, if you have bad partitioning, it makes routing more difficult. It means a lot more swap gates will be needed. And so cleaning up the partitioning, and we do it twice. We do it once all to all, not assuming any topology. So that's kind of an all connected topology. And then we do it again after routing. Okay, so this result, basically, we look at the quantum circuit as a directed acyclic graph, okay? And that specifically matches with this nice math paper from, 20, 30 years ago that covered how to calculate all the closed convex sets. Okay, so this is if you're doing topological sorting of a directed acyclic graph, you're going to have regions which are neighbors to each other, and these are these convex sets. And so this paper enabled an algorithm that allows you to enumerate all convex sets that are connected. Obviously, in a quantum circuit, if things are not connected, there's not too much use to bundling things together in such a way. And this paper had both algorithms, connected and unconnected, so for closed or non-closed terminology here. So basically the candidates are limited though. And the reason we can do this is because we don't find all convex sets, we find only ones less than this qubit max, 3 to 5 qubits. And then we turn it into the exact cover integer linear programming problem. And this turned out, and nobody had really discovered this ever before, which is interesting, that you can actually find the optimal partitions, so the least number of partitions possible, by just generating all of them and then running this simple ILP solver equation, right? It's saying that all the gates are selected once, and you can also minimize some cost function. And it's pretty simple. And solvers like Gurobi are excellent at solving such a problem. Uh, so, okay, so it's basically practical because of these modern ILP solvers, and we can use this to generate optimal partitions. And we can also just take all the partitions and maybe generate some information, weights about them, which is what we're going to do in the next result. And we can use them to, use these weights here to actually find a circuit that meets some optimization goal. Okay, or find a partitioning that meets an optimization goal. Okay, so the 3 to 5 qubits is pretty much a practical limitation. The number of convex sets and stuff will start to blow up if you go beyond that. But we can do 3 to 5 qubits for sure with partitioning. So, and the details of using BFS and how it works are not super important. However, if you notice in this workflow here, we have this cycle-free global blocks. Well, that was a little surprise that once you get your optimal partition, on occasion, those optimal partitions could have cycles. And that's kind of meaningless when you have a quantum circuit partitions with cycles between them. So you have to break these cycles, and there's techniques, especially using ILP solvers with callback functions, so you can quickly break those and you can get a valid solution. Okay, so that's there's several techniques possible here, and yeah. All right, so yeah, kind of to finish with this result, the ILP solver will actually, guarantee that every gate is covered once, and this the cycle cuts are the cycle elimination cuts are going to deal with that one way or another, whether you use callbacks, whether you have to run the ILP multiple times and start banning bad solutions, or you try to predetermine all the cycles, which is very expensive. But the callback works excellent, and that's what we're using. So this also is a technique that we extended BQSKit's SecPAM algorithm. This is their algorithm for routing a circuit. Okay, and their routing uses quick partitioning, and our solution is basically as fast as theirs, and yet it's finding the global optimum minimum partitions, whereas theirs is using some really rough heuristic. And so we can actually kind of improve other tools by integrating it. Okay, now we're going to move on to a completely different result, because now once we have all these partitions, well, if we actually want to decompose a circuit, okay, and we've got in our Squander library, and I've put a link on the website. If you look at the contribution, you can find it, and it's our project where we do this. And so we've implemented all of this, and basically, if we want to do something that will take advantage of these partitions, we're going to want to take all the gates in the circuit, turn them into CNOTs first off. So if you have any, 2 qubit, 3 qubit gates, we have exact decompositions for every single one into CNOT. And then at that point, we're going to try to find another circuit using CNOTs with less CNOT. Okay, we're going to try to find an alternative circuit. And we need to optimize that. And that's where we get the big win, because now we have the weights that we can use in the previous result. So we use BFGS to do our optimization. We have a highly optimized BFGS algorithm based on Powell's method. And we have this basically is going to use this operator Schmidt rank. Okay, that's what OSR stands for here. You see OSR guided. This is the operator Schmidt rank. Basically, you're going to take a circuit along all of its different bipartitions, and I'm going to kind of go into more detail here about this, but you're going to take it and on all the different bipartitions, while you're doing BFGS, you're going to have a special cost function. And that cost function is going to take the operator Schmidt rank, where you separate the circuit into two bipartitions and you run the singular value decomposition. And the rank of the resultant vector is going to give you, if you take the logarithm, the minimum number of C naughts. So now you have a ton of different bipartitions, and you know for each of those bipartitions, the minimum number of C naughts needed to satisfy that partition. And so this search basically is going to be guided by this deep in its cost function. And in the BFGS, we know how to calculate the gradient even with singular value decomposition fault. It's no problem. So we calculate all the gradients, so we can do this very efficiently. And we go kind of cut by cut to try to make the cost function as simple as possible. We don't want to try to necessarily optimize all cuts. I've tried that. It didn't work as well. It's just single cut. Okay, so we go one cut at a time. And then after we get all the data from all of this, we find, the best result we're going to find. Then we brute force some C0 solution. So you know that, okay, you need, 2 C0s between a partition with qubit 0, 1 and the other one is the qubit 2, right? If it's a 3-qubit partition, you have 0, 1 here, 2. And then you have another with, say, 0, 2, and 1, right? And so you know the different counts, and then you can try to brute force an actual C0 solution. And when you do that, and it's easy to do, by the way, to brute force this, it's with 3 to 5 qubits, it's fine. Then we can actually compute a score. Okay, so not only do we find the minimum number of C0s that are needed to actually satisfy all these cuts, but we can create a score. And the scoring technique uses the idea of kappa. We call kappa, but here it's represented by S. But basically, we take a surplus. So when we calculate all these different cuts, we take a surplus for how much higher they are than the expected value for each one. Okay, so this is kind of, we take all these different C0 counts, and then we calculate how much over they are. And when we see how much over they are, we multiply that by kappa, which is I think we mentioned it here. It is, okay, well, it's a bit complicated how we do this, but eventually this is going to be the scoring function. And the kappa is the weighted tail sum, essentially, of the vector from singular value decomposition, because basically you know the rank, right? You know the rank from taking the number of non-zero elements of that result from singular value decomposition. But we want to know, like, if the rank is, 2 or 3, we want to know, okay, you're in between the rank. Maybe you're at 2.3 or 2.7. So this is a way to estimate how far you are to getting to the next rank. Okay, and this is really important. And the reason it's so important is because there's a plateau with trying to solve this. So you end up on a huge plateau, and you really need to try to guide placing the next gates, which is what we're doing. We're just doing a graph search, trying to place gates everywhere. So we try to place every single type of gate at every single position in the current circuit. And then we take if we can find a better result than the current circuit with however many C0s we have, then we take a step. So this is also an optimistic algorithm. So if, like, let's say we place 1 C0 at all the different positions, and this metrics never improve, well, if they never improve, then we take 2 C0s at every position, which of course, combinatorial, much more expensive, but that's the necessary thing to try to get off the plateau, along with using all of these different metrics. So then basically the minimum number of C0s, then this idea of a surplus metric, and then finally the final profile tiebreaker here is the just the kappa without using the surplus, right? So we try to maximize the information that we have. Okay, so the results here, well, this I'm fixing right now. Okay, we're adding float 32, so we're using float 64. We're trying to get some 2x speedups, doing tons of optimization work now in Squander, because we do want to actually have the times more competitive. The partitioning is fast, but the OSR stuff, it takes time. But our numbers are a lot better. than BQSKit, who's our main competitor in this area, and KISSKit as well. But BQSKit's more the real competitor. So these are just the various results run on various size circuits. So you can see we're doing circuits that we can't even like, simulate classically because there's so many qubits. And you can see the times can get pretty absurd, but sometimes our times are pretty low. But this is going to be improved. So that's kind of the last step here, is just to get these times down. But the results we're getting are hands down beating our competitors. So, well, this is interesting too, because it's a highly parallel search algorithm. I mean, we have all the partitions, and then for each partition, we have all the different places in the current circuit to place the next C knots while we're optimizing some U3 gates around it each time with this OSR guided algorithm. So there's a lot of detail. It's quite complicated, so I can't, I don't have time to talk about all of it. So, okay, I'm just going to summarize this because I think I'm running out of time here. So, okay, basically the flow here, we enumerate all the partitions, and we can solve the global partitioning. Actually, there's different strategies. So this is one strategy where we just, if we want a really fast result, we take the just best partition at that point, and then we only optimize that. Or we can we can invert the order here of these two, and we can run this one first on all the partitions, and then use those as weights for this. So there's two options here. If we really want the fast result, but it won't be as good quality. So, and then we're going to eventually get a much better circuit. And in fact, we can run this again and again and again, because one of the weird things about doing 3 to 5 qubit partitions is if you optimize a bunch of 3 qubit partitions, and then you take that result, you will find new 3 qubit partitions that can further be optimized because they're obviously able to combine with their neighbors. So yeah, so if the takeaway from the talk here, basically the quality of the partitioning is going to be the kind of key thing that drives all of this. Exact set cover is a great problem if you can ever find it anywhere. Just run to a modern ILP solvers. You will get it solved. If you can find it in any problem, this is going to be an easy practical win. And OSR, using this as a guidance tool for a cost function, unlike the normal Hilbert-Schmidt and other techniques, this is a technique to minimize entanglement, and that's the hardest part of the problem. Okay, so once we minimize the entanglement, we can get then we can run a Hilbert-Schmidt at the very end. I mean, I don't go into all these details, but yeah. So that's the main thing, is that this technique has never really been used for this purpose before, and so we finally kind of formalized this. Yeah. So okay, thank you very much. Any questions?
Let's thank Gregory. Okay, we have time for one short question. So
maybe it's not short, but so in slide 11, maybe you presented these algorithms which you have compressed, so to say. And my question is that, okay, so for example, let's take Grover. And is it possible to come up with a generic statement about Grover's algorithm regarding the gate count? So can you search for like better decompositions in general and like make a theoretic statement?
Okay, yeah, thanks for the question. This so in terms of these types of algorithms, I think a lot of these have already been researched to the point that we can kind of assume that they're pretty optimized. But yeah, we could take this, we would have to try, because again, we're only doing 3 to 5 qubit partitions, so we're not guaranteed to get global optimum. But yeah, we could try to find patterns, but it's still going to take hard work, because you're going to have to start optimizing, at different sizes, and then trying to identify what the pattern is for the simplifications, if any exist. But I think a lot of these types of famous algorithms have had so much work put into them that it's not very likely, was our conclusion, because I also thought about this, and yeah, it's not too likely to find optimization opportunities on these famous ones. Yeah.
Thank you.
Peter has a comment, but you are using your own time.
Sorry.
I have just a small comment. So the Grover algorithm uses Oracle, which is completely up to you how you implement the Oracle. So I think there is much room to improve on a given Grover algorithm implemented on the quantum hardware. It's not like a Fourier transform, which is given.
Yeah. And I guess it's too because if we consider topologies, obviously, like there are papers though that give specific ways to encode Grover's algorithm, I believe. So I mean, but yeah, with specific topologies and stuff, probably finding a pattern would be very useful. So yeah, that would also be a good application.
Okay, thank you. So we have to move on. So let's thanks Gregory again.